The theme of my talk is, in my opinion, the most general approach to the theory of Hausdorff operator. This talk is based on my preprint in archive, and I refer for details to this preprint. The first form of the Hilbert, of the Hausdorff operator appeared in the works of Garabedian, Rogozinsky, and Hardy in 1940s, and looks as follows. Here mu is an arbitrary measure on the segment 0, 1. F is a function on the semi-axis, on the positive semi-axis. So I call this operator Hausdorff operator on the ray 0, infinity, or Hausdorff operator on semi-axis. The name Hausdorff is due to the fact that this is a natural continuous analog of the Hausdorff summation method for series and integrals. Here, the integrand is a function f, which is composed with the next very simple functions a of u. This is a dilation of the ray 0, infinity for each positive u. In this century, the theory of Hausdorff operators born again, and during last 2 decades, many new integral operators appeared under the name Hausdorff operator. Now I want to list several of them. Sorry. Сюда? Не работает. Что ж такое? Да. Okay. The first example is the so-called Hausdorff operator multidimensional, or Hausdorff operator on the Euclidean space. Here, phi is a given locally integrable function, the so-called kernel. Du is Lebesgue measure on Rm. X runs over another Euclidean space, Rn. And AU is a family of non-singular n by n real matrices. And this definition was given Brown and Morris in 2002. And the first non-trivial result for this operator due to Lerner and Lifland in 2007. Here, the function f is composed with the map A of u, which is the multiplication of the by the matrix singular n by n matrix A of u. And this map is, of course, additive homeomorphism of the topological group Rn. The next example is called Hausdorff operator on the upper half plane. This definition was given by Stilgianis in 2020. Here, phi, a kernel, is as usual the integrable function. Du is a measure on the half line, 0, infinity. F is a function in the upper half plane. And in this case, the function f is composed with the following map A of u, which is a bibliomorphic map of the upper half plane. And the next example is so-called Hausdorff operator on the unit disk, or a Hausdorff zoo operator. It has the following form: phi of u, as usual, is mu is an arbitrary measure on the unit disk D in the complex plane. Phi is locally integrable with respect to mu function on D, and F is some function, complex valued function on D. This operator was introduced and studied by me in 2021. And in this case, the function f is composed with the following map, which is called involutive Möbius transformations of the disk. And the next example was introduced in most generality by Alexey Nikolaevich Karapetyan's, and it was studied in the special cases by Professor Petrov in 2006. And here we have the measure mu. This is a positive measure on the interval minus 1, 1. Phi is a given kernel, and f is composed with the following functions. In this case, in the case of the interval, u is, of course, also a point in this interval. And in this case, this is a homeomorphism of this interval as a topological space and an order preserved bijection if we consider this interval as an ordered space. And the last example is more complicated. A Hausdorff operator on the Heisenberg group H(n). This definition due to Guo, Sun, and Zhao, 2015. And here H(n) n is, of course, a Heisenberg group. Du denotes the Haar measure. Phi is a given kernel, and delta sub r for all real r is so-called dilations of the Heisenberg group. The Heisenberg group, the underlying manifold of the Heisenberg group is the following Cartesian product, and for an arbitrary point VW T from this group, for this product, delta sub r, the dilation, acts very simple in the following form. And now I want to give the general approach that covers all previous examples and a lot of others. So let we have an arbitrary category K and two objects R and S in this category, and we consider all morphisms. More RS denotes the set, as usual, of all morphisms, and it should say that for the special case where R equals to S, I consider not all morphisms, but automorphisms of this set S, object S in the category K, sorry. And then let me introduce an arbitrary measure space omega mu, and the family of morphisms A, a map from omega to the set of all morphisms in this category. So the general definition I propose is as follows. Let V an arbitrary topological vector space, F a function defined on the set S. S will be a set, not only the object on this category, but a set. And F is a function, V-valued function on S. Then we choose and fix an arbitrary kernel phi. This is a locally measurable function with respect to mu on omega. And here f is composed with the following function a of u of x. For each u, a of u is a morphism of this category, and this is a value at the point x from R. All previous 6 examples and all forthcoming examples correspond to the case where R equals to S and A of U is a set of automorphisms of our set S. Let's come back to the beginning. For example, in the Hausdorff operator on the Euclidean space, the multiplication by non-singular matrix is a general form of the automorphisms of the Rn as an additive topological group. And in this example, A of U is automorphisms of the upper half plane as a one-dimensional complex manifold. And in this example, A of U Möbius, involutive Möbius transformations is automorphisms of the unit disk as a one-dimensional complex manifold. In this case, our A of U is automorphisms of the interval -1, 1 as a topological space, and automorphisms of this interval -1 also as an ordered, a linear ordered space. Here, dilations, as is well known, is automorphisms of the topological Heisenberg group Rn. It is interesting that the general definition covers also several classical operators that at first glance are not related to Hausdorff operators. I'll give several examples. First of all, the Hankel integral operator. We take kernel phi. Here S is R with standard Euclidean metric. A of U of x is U minus x, of course, preserves the Euclidean, classical Euclidean distance on the line. And if we take, as usual in the theory of Hankel integral operators, function f, which is supported on R plus, then our general definition turns into the classical definition of the Hankel integral operator. In the Hankel operator is the integral form on the half line. The next example, we take the same S and omega R with Euclidean metric and Lebesgue measure, the same A of U of x minus U, but the kernel is the so-called Cauchy kernel. In this case, the general definition turns into the classical Hilbert transform of the functions on the line. And the discrete Hilbert transform also fits into our general definition. Here we integrate with respect to Lebesgue measure, and if we take in the general definition such as omega R phi, but measure is discrete, we get the discrete Hilbert transform. And the next example, let S and G and omega be a multiplicative group equipped with right invariant metric. A of U is a set of all right translations in G. These translations we took in right invariant metric, so these translations is automorphisms in the category of metric spaces. The kernel identically 1, and in this case, the general definition turns into the well-known classical operator of convolution with a measure. Other examples, Hausdorff operators on topological groups, they are homogeneous spaces, they are double cassette spaces, various averaging operators, etc., also fit into the general definition. Now I want to present a result. We can choose a concrete category, say category of topological spaces, metric spaces, topological groups, and so on and so on. But I want to present a result for general category K. In order to do this, I assume that our set S also is a quasimetric measure space with quasimetric rho and positive Radon measure nu. And for any untrivial result, we have here several structures. The structure of category K, the structure of quasi-metric space with metric rho, the structure with a measure space with metric mu, and also we have a measure mu in the general definition of the Hausdorff operator. So all these structures must be consistent with each other. More precisely, I want to give definitions how our family A of U of automorphisms of the set S in the category K is in agreement with the quasi-metric rho on the set S with the measure nu on the set S and with the measure mu in the definition of our general Hausdorff operator. So I'll give several definitions. I assume that our omega is a sigma compact quasi-metric measure space with positive random measure mu. And we say that the family of automorphisms A of U of our set S in the category K agrees with the quasi-metric rho in S, quasi-metric rho in S, if there exists such mu measurable function K of U on omega, that for each U and for each positive R, the pre-image of the ball with respect to quasi-metric rho centered at X with radius R contains in some other ball whose radius with some point X prime as a center, whose radius have the form K of U multiplied by R. The point here is that these coefficients depends only on U, in fact on A at U, but do not depend on X and on R. And the next definition, we say that the family of automorphisms A of U agrees with the measure nu if there is such measurable functions M on omega non-negative, then the following equality holds. The measure nu of the pre-image of an arbitrary measurable finite measure set E equals to a M of U multiplied by nu of E. Very often this condition holds. For example, if K is a category of locally compact topological groups, and nu is the higher measure of this group, then it is well known that this holds, and M at U is the so-called modulus of the automorphism A of U. And the last definition, how our set of automorphisms agrees with measure mu, we say that this set of automorphisms is mu measurable if for each fixed point x, the function A of U of x is measurable as a map from the measure space omega mu to the measure space S nu. So I want to present the result about the boundedness of our general Hausdorff operator in the atomic Hardy space in the sense of Kaufman and Weiss. So I want the so-called doubling condition. We say that the metric measure space S rho nu is doubling, or in other words, nu is a doubling measure. If there is such constant C, that the new measure of the ball with radius 2r is less or equal C multiplied by the measure ball of radius r. So C does not depend on x and on r. And the smallest C is called the doubling constant. And its logarithm is called the homogeneous dimension, or the homogeneous dimension of this doubling measure space. As regards the space H1 on this quasi-metric measure space, which is doubling, I refer to the famous paper of Kaufman and Weiss in Bulletin. They introduced the so-called atoms on this arbitrary doubling quasimetric measure space, and in terms of atoms introduced the Hardy space H1. So the general result looks as follows. Let S rho nu be a quasimetric measure space with a doubling condition. H1 on S suppose be separable, and let a family of automorphisms are mu nu measurable, agrees with rho, agrees with nu. Then if the integral in the right hand side of this inequality converges, then our general operator, Hausdorff operator HF A mu, is bounded in the Hardy space H1, and its norm satisfies the following estimate. Thank you for your attention.